want to talk about one of the major misconceptions in physics about one of the major elementary particles which constitutes everything around us, the electron. And that misconception is a misconception about the size of the electron and our knowledge of the size of the electron. Now, for many people, they think the electron is very, very small. And it is, in a certain sense, very, very small. Its Compton wavelength is 2.43 10 to the minus 12 meters. So it's about a couple of percent of an angstrom, a couple of percent of the size of an atom. So in that sense, it's a very, very small thing. But the misconception I'm talking about is people who think that it's far smaller still. That experiment has shown that the electron is small at the scale which is 1,000,000 times smaller than that, 10 to the minus 18 meters. And I see this coming up often in talks. And as an ex-high-energy physicist, this was the kind of thing which we sort of believed as being implicitly true for electrons, that they were extremely small, at the order of 10 to the minus 18 meters. But in fact, that's not the case. It's not the case even for an electron in free space. The thing is that why do we say that it is so small in high-energy physics experiments? Well, the reason for that is that if you do a scattering experiment with an electron, electrons on electrons, they act as though they are that small down to that size. So in that sense, the electron acts like a point particle down to 10 to the minus 18 meters. But why am I saying as a physicist as well that it is absolutely not a point particle of 10 to the minus 18 meters? Well, there are a couple of major reasons for that. One of them is that the electron has a spin and it has a mass. And even at the speed of light, spinning at 10 to the minus 18 meters, the electron could not have the kind of spin that it has. That's one thing. The other major thing is the electron has a charge. Now, the charge gives an electric field, an inverse square electric field, which is well known. The charge on the electron is extremely well known. But a field also constitutes an energy density. The energy density in the electric field in SI units is a half epsilon times the electric field squared, half epsilon E squared. And you can calculate the mass energy in the field very simply with a simple integral. And it turns out that if you integrate down to what's called the classical radius of the electron, which is a small number again, 2.8 10 to the minus 15 meters, at that stage, you have got all of the mass of the electron accounted for by its field alone. If you keep on integrating down to zero, that mass of the electric field of the electron goes to infinity. Now, electrons do not have infinite mass. They cannot be smaller than 10 to the minus 15 meters and maintain their mass. They have to be larger than that, even in free space. Compton wavelength, of course, 2 times 10 to the minus 12 meters is a lot larger than that. It's the wavelength of an electron in free space. So that's the inner wavelength of an electron in free space. But electrons are actually usually far bigger than that too. As a professional physicist at CERN, did scattering experiments where electrons, leptons, acted like point particles indeed. But as a professional physicist working in the solid state, I did experiments on those very same kind of electrons and found them to be far larger in the sense that you could measure them, measure their charge profile to be much larger. So there's a paper, Williamson et al., 1990, Physical Review, where I looked at the electron profile and found the electron profile in a semiconductor device to be tens of nanometers. These things were very, very much larger. So the electron is not then a very small thing, not small even compared to design rules now for semiconductor chips. Silicon chips, they're down smaller than that size. So the electron's no longer really in the solid state a small thing, and it cannot really be a small thing in the sense of the way that it's understood at CERN. So why is it that it's thought to be so small? It's thought to be so small because of the way it acts in scattering. And that way is inverse square down to very, very short distances, apparently. But it is sufficient that it merely be inverse square and a single object for that thing to have that kind of property, which of course is true for the electron field. That doesn't make it a point object. It means that it acts as a point object in terms of the way that it interacts with other things. And the reason for that is explained in some of the papers which you'll find on Quicycle.com website if you want to look into some of the mathematics of that. Thank you very much.